actually a last year PhD student from the CNCL lab. And this is my topic today. Today I'll be introducing one of my work, Understanding Credibility of Adversarial Examples Against Smart Grid. And this work is collaborated with my supervisor, Professor Tan Rui, Ren Chao, and my co-supervisor, Professor Xu Yan. Nowadays, the traditional power grids are evolving into smart grids to deal with new challenges caused by the deployment of renewable energy, distributed generation, demand response, and so on. And deep learning technologies are increasingly adopted for enhancing various smart grid capabilities, including stability assessment, load forecasting, and fault detection. Although deep learning shows appealing efficiency in learning the sophisticated patterns from the big data generated by the power grids, these deep models are also vulnerable to adversarial examples. Adversarial examples are crafted inputs that aim to mislead the target deep models to give wrong predictions by adding very small perturbations to the clean inputs. This paper, for example, studies the adversarial example attack against the load forecasting model. Since power grid is a safety-critical system, wrong outputs of the DNNs used in the power grid applications may lead to catastrophic consequences such as blackout. Therefore, the vulnerability of DNNs applied in safety-critical grid applications need to be carefully considered. Various adversarial example algorithms have been proposed and shown effective in the field of computer vision, and the corresponding vulnerability analysis have been conducted in the safety-critical systems. So you may be wondering why we need to analyze the vulnerability in the DNN-based grid applications. Various adversarial example algorithms have been proposed and shown effective in the field of computer vision, and the corresponding, in the left figures, adversarial stickers are pasted on the stop sign and successfully mislead the traffic sign recognition model to output the speed limit sign prediction. In the CV applications similar to this example, the original clean inputs are static so that the attack can be computed and deployed in advance. These requirements of obtaining and modifying the clean original inputs are reasonable in the CV tasks. However, in smart grid, where the data is generated and analyzed dynamically, the requirements of real-time eavesdropping and data tampering for attack construction is sometimes too stringent. Therefore, we cannot simply transfer the worry from the CV applications to smart grids without discrimination, and a credibility analysis of the adversarial example attacks in the DNN-based grid applications is needed. First, I'll briefly explain what are adversarial examples. The construction of adversarial example can be formulated as this constraint optimization problem. The goal is to minimize the distance between the original sample and the adversarial sample, subject to that the output of the neural networks is different from the original label. Here's a table of 6 representative adversarial example construction methods that are frequently evaluated in the literature. The first column tells the name of the attack. The second column tells whether the attack is input-specific or universal. The former means the adversarial perturbation is effective against a particular clean example, and the latter means the perturbation is universal for many clean examples. The third column shows the computation needed for the attack construction. One shot means only a single computation step using closed-form formula is needed. Iterative means an iterative search process is applied. The last column shows the knowledge about the target model required by the attack construction. The white box methods require full knowledge about the DNN's internal, including its architecture and weights. And the black box attack only requires the access to run the model without knowing its internals. And the white and black box label means the attack is effective on the target model when constructed based on the target model's parameters. When the parameters are not available, The attack can also be constructed based on a different surrogate model. This surrogate model may be trained by obtaining the training dataset or querying the black box target model. And the goal of this work is to analyze the requirement and study the credibility of adversarial attacks against the power grid-based DNN applications. In this work, we systematically investigate the requirements and discuss the credibility of the 6 representative adversarial example attacks shown in the previous slide for a case study of the DNN-based online voltage stability assessment. The voltage assessment is based on the New England 10 machine 39-bus system shown on the left. In particular, we perform extensive offline time domain to generate voltage trajectories, and in each simulation, a 3-phase fault that lasts for a random time duration ranging from 0.1 to 0.3 seconds is injected to a randomly selected bus. The fault is later cleared by a single or double transmission line stripping, and each sample consists 1 second long post-fault voltage trajectories of all the 39 buses and labeled with stable or unstable. The figure on the right shows 2 examples of stable and unstable situation. We can see that after the fault clearance, in the stable situation, the voltages of all buses restore to an acceptable level, while in the unstable situation, the voltage remain far away from the nominal values. And we train a VSA DNN to look at the 1 second long voltage trajectories after the fault clearance and predict whether the voltage will be stable or unstable in the future. In what follows, I will present how we analyze the credibility for each attack through our investigation experiments based on the VSA case study. The first step for the analysis is to find out the requirement for crafting each attack. According to our study, the requirements contain read access and write access to the clean voltage measurements, knowledge about the DNN's internals, and the access to the DNN's training data. In the VSA case study, the number of buses that the attacker needs to tamper with is a key requirement and indicates the difficulty to craft the attack. In this slide, I will introduce how we implement the partial adversarial perturbation to satisfy different intensity of the write access requirement. The formulation for the partial perturbation construction is to minimize the distance between the original sample and the adversarial sample, subject to that the output of the neural net is different from the original label, while only the input dimensions of X corresponding to the L buses to be attacked are modified. To implement such partial attack, we apply a mask M. M is a matrix that has unit values in the area corresponding to the L buses where the adversarial perturbations are added, and 0 values in the area where no perturbation is added. During the attack construction, the computed adversarial perturbation in each iteration is multiplied by M and added to each clean example. And we implement this partial perturbation in our experiments. In this figure, the DNN accuracies under white box attacks are presented. White box means the attacks are constructed based on the target VSA DNN's parameter. Y-axis of this figure is the accuracy, and x-axis is the number of attacked bus L. First, let's look at the result under the input-specific attacks. When L increase from 1 to 15, all attacks are not very effective. And when L is 20, which means around 50% of the bus voltage measurements are attacked, the accuracy under the FGSM and PGD attacks have significant drops. When L is large enough, Deep 4 and CNW attacks are both very effective. Although Deep 4 and CNW are considered very powerful in the field of computer vision, in the context of VSA, they need to tamper with too many bus voltage measurements, which implies a very high attack overhead. For the universal attacks, When tampering with 20 and 25 bus voltage trajectories, the UAN and UAP attacks become effective. Under the black box setting, the input-specific FGSN attack still can significantly decrease DNN's accuracy when tampering with around half of the bus voltage readings. Other input-specific attacks are less effective as under the white box setting. These results show that the FGSN is the more transferable among all the considered attacks. This is because the FGSN underfits the surrogate DNN and has higher transferability to the target DNN, while the others overfit the surrogate and therefore have reduced effectiveness against the target DNN. For the universal attacks, the UAP and UAN achieve similar effectiveness as under the white box setting. And this indicates that the universal attacks do not require the target DNN's internal to be effective. This also suggests that the two universal attacks are more transferable compared with the input-specific attacks considered. In this table, we summarize the attack effectiveness and requirements against VSA. And the table presented the minimal set of requirements for each of the attack to render the attack construction effective. The first 4 rows are the input-specific attacks, and the last 2 rows are the universal attacks. From the table, we can see that all the input-specific attacks require read access to the original clean bus voltage trajectories to conduct attack, while the universal attacks do not have this requirement. And all the attack can be effective when only tamper with part of the bus voltage trajectories, except for the CNW attack. In terms of the knowledge needed for the attack construction, the FGSN and PGD attack only require DNN's internal under the white box setting or the training dataset under the black box setting, and this is marked by either in the table. For the D4 and CNW attacks, the DNN's internal is a must for generating effective adversarial examples. Both UAP and UAN need the training dataset to compute universal adversarial perturbation, and the DNN internal is not a must to generate effective attack. Now we understand the requirements to conduct each of the attack. In what follows, I will discuss about the credibility of these requirements in detail. First, I will discuss the attack credibility in terms of the write access requirement. To launch both input-specific and the universal attacks, the ability to tamper with bus voltage traces is a must. From the experiments, we observed that we only need to compromise about half of the buses to significantly decrease the DNN's accuracy. The costs increase when tampering with more and more buses, but the attack effectiveness doesn't have significant improvement. Therefore, obtaining the right access to compromise about half of the buses is a rule of thumb for the attacker. And there are 3 possible ways to implement the attacks. The first is to hack into the enterprise network of the power grid control center. However, the attacker with such capability should directly subvert the VSA results instead of resorting to the adversarial example attack. And the second way is to compromise the communication links from the buses to the control center. To launch such attack, on one hand, the attacker should be able to intercept the network transmission of the clean voltage readings on the communication path and transmit the maliciously perturbed voltage traces to the control center without causing any suspicion. On the other hand, the attacker may need to breach some cryptographic protection of the communication link. The third way is to manipulate the analog sensors. For example, by using remote electromagnetic inferences. Such capability has been demonstrated in the literature. To summarize, the last two attack implementations are feasible and cannot be completely ignored, although they require very sophisticated design and extensive skills. In terms of the read access requirements, for the input-specific attacks, the attacker may need to wait until the clean voltage trajectories is generated in order to compute the input-specific perturbation. Therefore, the sensor manipulation is not applicable, and the attacker must inject the attack through the communication links from the buses to the control center, which needs sophisticated design and is less credible. And the construction of the universal attacks is independent of the real-time clean samples. So the attackers can launch the attack by either manipulating sensor readings, communication links. So the universal attacks is much more credible. Static knowledge required by the attack construction includes the target DNN's internal, the training data, or the black box target DNN. From our experiments, at least one of them is needed to construct effective adversarial attacks. And because these pieces of information are static, they can be obtained in the scenario of the advanced persistent threat. For example, the attacker may use social engineering against employees of the grid operator to obtain this static information. So preserving the confidentiality of the static knowledge of the power system is a very weak defense. And during our study, we observed that the universal adversarial examples has the same credibility as the widely studied false data injection attack against the power grid estimation. This is the formulation for the FDI attack vector. Here, A is the FDI attack vector. H is a constant matrix for state estimation determined by the power grid topology and the line impedance. And C is an arbitrary vector. From this formulation, the attack vector is computed independently from the real-time power flow. And for the universal adversarial example, it also needs a static training dataset, which is similar to H, and the construction of the universal attack is independent of the real-time system measurements. So the universal adversarial example attack has the same credibility as the FDI attack. In the following part of this presentation, I will show how the 6 adversarial attacks perform under different defense mechanisms. In this work, we employ adversarial training and the APE-GAN as defense methods to evaluate their effectiveness in the VSA case study. Adversarial training is a model hardening defense that attempts to improve model robustness by including adversarial examples with their correct labels into the training dataset for model training. In this paper, we include the PGD adversarial training. We include the PGD adversarial examples during the adversarial training because existing studies and the competition results have shown that the PGD adversarial training gives state-of-the-art performance on various benchmarks. We also deploy APE-GAN, which is an input cleansing defense that trains a generator to cleanse the input adversarial example, and output is benign counterpart. The generator is trained under the GAN setting. We also try to combine these two defenses. Our experiment results shows that the adversarial training has the best defense performance. So in the following presentation, I will only show the defense performance of the adversarial training. This figure shows the DNN's accuracy under white box attacks with PGD adversarial training. we can see that for almost all of the attacks, the adversarial training is very effective in protecting the VSA DNN, except for the less credible deep fall attack. This dashed line here represents the deep fall results with no defense, and we can see that the accuracy is improved with the adversarial training. And under the black box setting, all attacks are not effective against the adversarially hardened DNN. And for the more credible universal UAP and UAP attacks, under both white box and black box settings, the universal training can effectively protect the target VSA DNNs. So to summarize, this paper obtains these three conclusions. And this is all of my presentation today. Thank you for listening.
Song-Chun, thank you so much. That was a very precise presentation from your side. And I think I'm not very familiar with the smart grid, in fact. So let's keep this slide shared for now. And then we'll start receiving the queries directly from the audience. And the audience now can directly unmute themselves and put forward their queries, concerns to Song-Chun. So if there is anyone wants to have a query.
Hello.
Hello.
I'm Hao Nan, and I want to ask a question.
Sure. Please go ahead.
Could you turn to slide 9?
Slide 9?
Yeah. Yeah. Here we can see the method of C and W is very poor. Whether you address the parameter of C and W, like a learning rate or step size.
You mean whether I optimize the C and W attack for this case study?
Yeah.
Yeah, I did some search using I think I used the repo provided by the author, and I did some search over the hyperparameter of the attack construction, and from my observation that they have similar attack effectiveness. I mean, the hyperparameters doesn't have much influence on the attack successful rate.
Okay, thank you. Because I used to do some adversarial learning projects on image, and I don't think CW will be very poorly compared to PGD. I think usually they are very similar.
Because for the image, if you attack the image, you can modify every pixel of the image, right?
Yeah.
Then if you can modify every pixel of the image, I believe CNW will have very high attack successful rate, because you can see from here, if I attack all of the buses, and CNW is still very powerful, but if in the case of the VSA situation, it's very difficult to attack every bus voltage trajectories, because it will brings a very high attack overhead.
Okay, thank you.
Yeah, I mean, it's a very powerful attack if you can modify every dimensions of the input data. And I think your understanding is not wrong.
Yeah, it's fine if you try to try the different parameter of CW. I think it makes sense.
Yeah, because it's an optimization method, right?
Yeah.
So I think it's understandable that it cannot have very high successful rate if it cannot modify every dimensions of the input.
Okay, thank you.
Thank you, Hannah, I guess. So is there anyone having concern or queries? Please, you can unmute yourself and start asking question. Chun, can I put one layman question? So what is the application side of your research? I mean, where can people apply your research?
Oh yeah, because now the traditional power grid is evolving into smart grid, right? And people are studying to integrate deep learnings into the safety critical or mission critical power smart grid. So
Right.
I think it's very important to carefully address the potential vulnerability in these systems if you really need to deploy deep learning. Yeah, and I think we don't have to from this study we don't need to worry too much from the adversarial example attack, because you can see that from my analysis, credibility analysis, the attack overhead is very high, and it's actually not very easy to have control over more than half of the bus voltage trajectories in a smart grid. So I think it's actually convey a good message to the smart grid designer.
Okay. Yep, I understood. Yep. So yeah, is there anyone having their queries? Or we can, yeah, someone is unmuting.
Yes, I have a query.
Yeah, please open.
Yeah, in this you tested against multiple real systems, right? Or have you tested just on theoretical basis? That is, how did you actually test on real grids?
Oh, so sorry.
Because that seems to be out of scope from academic point of view or academic institutes.
So he's asking about how can you practice in the real grid, right? Upon?
Yes. How did you conduct experiments on real grid? Because this seems to be way out of scope for from academic institutions. And all these experiments seems to be conducted on that voltage system, how the voltage stabilizes.
Oh, you mean how to conduct
the
attack in real systems?
Right. Yes.
Yeah, experiments. Yes.
I actually let me. Yeah. Actually, I think it's not difficult to conduct adversarial attack in this real system, because yeah, you can see from this slides we have 3 possible ways to conduct the attack. And for example, maybe we can compromise the communication links using some cyber attack techniques, or we can manipulate the smart meters or some sensor at the customer side to add the attack. Did I answer your question?
I mean, my query was, how will it exactly resemble these 3 different types of attacks? You need to conduct experiments to demonstrate the effectiveness of your methods, correct? So if like, for example, if it's hacked into control center, you first need to launch an attack that's hacked into a control center and then demonstrate the effectiveness of DNNs to prevent the adversarial attacks. How did you actually conduct the experiments for this? Did you actually do anything of that hacking or something like that?
It wasn't actually actual hacking. I basically just I generate data through the simulation, and I compute adversarial example using different algorithms, and I prove the effectiveness of the adversarial examples. But I think to deploy the attack is actually demonstrated feasible in the literature. So my point in this paper is how effective is this specific type of adversarial examples in the case study of the VSA. Yeah, I didn't launch the actual attack.
Okay, so
Right.
Formulation of the attack and then test it.
Yeah.
Okay.
Okay, thank you, Apan, for the question. We have, I think, Amrit Paudel from Canada. Amrit, do you want to ask a question to Chun?
Yeah, I just want to add up something in the previous answer from Song Chun. Actually, I think the previous friend who asked question is Pankaj or someone, right?
Apan,
yeah. Actually, regarding this real, before that, I just want to thank you, Song, for a nice presentation. Actually, I did my PhD from NTU Singapore in 2020 from School of Electrical Engineering, and now I'm with UBC Canada. So it was nice presentation, but definitely regarding the practical implementation point of view, there are many gaps to be addressed in the future. And I just want to add the answer to the previous question from Apan that regarding the real implementation in the grid. Actually, we normally do not test this kind of algorithm in the real system. If we inject or implement this kind of attack in a real system, the system will be, if it goes everything okay, the system will be in control. But if something goes wrong, it will produce the delay stress effect in the power grid. So normally we make a prototype and we inject in a small scale like a microgrid. For example, we have in NTU School of Electrical Engineering, we have different microgrids. What we do normally, we inject in that kind of grid, and if it is okay, then we do simulation for increasing scale slowly. After that, only if it efficient or like feasible, then only we implement these technologies to protect the cyber attack, not to do the cyber attack.
Right.
Actually, we do not inject this for the cyber attack. We use this technique to be safe from cyber attack.
Cyber attack, absolutely agreed.
And one more thing is, I think there is a gap to address in the research, because this is the computationally intensive technique. So maybe improving the computational efficiency would be the next step in this research. Yeah, I do not have any other query, but just a few suggestions. Yeah.
Thank you, Amrit. Thank you for sharing your understanding. And yeah, I think Chun also did some kind of simulation. Am I right, Chun?
Yeah.
Right. Not in the real system. You have not tested in the real system. And it's almost like Amrit said, it's not a good idea to even test it in the real system, I guess, at least for the experiment.
Yeah.
Right.
Yeah.
Chun?
Actually, it's not good. But if she really wants to do some test in some prototypes, maybe she can collaborate with some guys from power system.
Okay.
I can give some name with the name of the people who work in the power system lab, and they have very good prototype and controller. So I think she can do some small scale prototype experiments that will give her a good publications and also good knowledge of the real prototype. Yeah.
Right, Amrit. Amrit, you mean the power? You mean power department school from NTU?
Yeah, School of Tripoli.
School of Tripoli, right? They're this power lab.
yeah, there are 3-4 power labs, and these kinds of research are also going on there. So you can collaborate there.
Yeah, that's a good suggestions, Amrit. Thank you so much. Maybe Chun in the future can contact Power Grid Lab in NTU right over here. Chun, thank you so much. I think we are almost done with our presentation, today's SLS talk, and I thank everyone who attended this presentation, and especially those who asked put queries, and Amrit, Apan, and then Hana from the audience side, and of course all the participants who attended this one. And Chun, I especially thank you so much. You came forward and then you had this wonderful talk sharing with you, and I'm really grateful to have you in this SLS talk. And I request all my friends out there to come forward and then give the presentation, share the research work they can recently have, or even if there is no any publications, they can simply come to the SLS platform and then share their research work. It doesn't have to be published somewhere in the conference or journal. It's not a mandatory kind of thing, but the SLS platform is there to help every one of us sharing our research work, and then getting feedbacks from all the friends out there. And it's really getting interesting. And Chun, it was a really wonderful to have your listening about your research work. Thank you so much, everyone, once again, and have a wonderful Friday and a wonderful weekend, guys. Thank you so much. We cannot receive any further queries for now, but if you are interested, maybe they can reach out to Song Chun, and she has, I think, GitHub website as well, and then the email address is right there in her website, or maybe you can visit to CNCL website and see her email address out there, and then you can write her and keep in touch with her regarding her research work. Once again, I encourage every one of you to inspire everyone here, and then share the research work in this SLS platform. It's for every one of us, by every one of us. Thank you so much once again. So we'll meet to the next SLS talk, guys. Thank you so much. Chun, thank you so much.
Thank you.
All right. Okay, guys. Bye-bye. See you next time. Yes. Thank you, guys.